dear students of class 12. Today we will be continuing with our coordination chapter. The topic is valence bond theory. So this theory was proposed by Pauli and is based on the hybridization that we have learned in class 11. So this theory, there are certain assumptions and the main points of this assumption is that here, as you know, in this complex coordination compound, what we have? We have metal and we have ligand. Now, this theory assumes that these ligands, they contain lone pair. They will give its lone pair to the metal vacant d orbital. Okay. Now, what you have to know is the metal atom or ion. Okay. Here, now it makes available its vacant orbitals for accepting of this lone pair of electron from the ligand. Now, how many orbitals will they make it available for the ligands? It depends upon its coordination number. So the first point is this metal, they contain vacant orbitals. In that vacant orbital, the lone pair of electron from the ligand is accepted. Now here, one more thing you have to learn is metals, they contain sp-d orbitals. Now this sp-d degenerate orbitals are made available for accepting this lone pair of electron from the ligands. Now here, this lone pair, whenever this lone pair of electron from ligand is accepted by the metal, then there is a formation of this sigma bond. Okay, formation of the bond, and this will fulfill the coordination valency of the metal ion or atom. Now let's discuss about the application, which is the main focus of this topic, application. And the questions from application part will be asked. So application of valence bond theory. Application of valence bond theory. So by using this theory, we will be able to predict the geometry, the hybridization, and as well as its magnetic characteristic, whether it's paramagnetic, whether it is diamagnetic. Okay, by using valence bond theory, we will be able to predict. Let me repeat it once again: the geometry, the hybridization, and also the magnetic character of the complex. So let's discuss about the tetrahedral complex first. So tetrahedral. So you know, now this tetrahedral complexes, from your previous knowledge, you know that they will be having this hybridization, sp3 hybridization. Whenever they have sp3 hybridization, then their geometry is what? Tetrahedral. Their hybridization is tetrahedral. Now let's take an example. Like here we have nickel carbonyl. You have NiCO4. That means here in this complex, what you have to know is you have to know in which oxidation state does this nickel is present in this complex. Now you know this, the electronic configuration of nickel: cobalt, nickel, copper, zinc. So nickel, whenever it is present as neutral atom, then its atomic number is 28. Okay, so this is the atomic number of nickel. So whenever we have to write its electronic configuration, then up to argon, it accounts for 18 electron. Okay, up to argon, it accounts for 18 electron. After that, you have d orbital 1, 2, 3, 4, 5. After that comes s orbital, then the p orbital. While filling this, you don't forget to use the Pauli principle that we have learned. So up to here it is 18. Then the s orbitals will occupy 2 electrons. Then it becomes what? 18 plus 2 is 20. How many electrons are left? 8 electrons. So first the d orbitals are filled singly. Okay, 5, 6, 7 and 8. Now, nickel in oxidation state, which is 0, neutral, will be having this electronic configuration. Okay, so in this complex, you have to remember that in this complex, this CO is a neutral ligand. In this complex as a whole, nickel will stay in oxidation state, which is 0. So since here, what you have to know? Carbonyl, this is for your knowledge. Okay, carbonyl is a strong field ligand. Now therefore it has power, since it is a strong field ligand, it has power to pair up these electrons. Means here one electron is present, here one electron is present. Now these electrons will come and get paired up with these two electrons. So whenever it is going to form the complex of this carbonyl, nickel carbonyl. Now therefore what happens is, in this complex, in complex nickel tetracarbonyl, the electrons gets paired up. D orbital 1, 2, 3, 4. It has 1, 2, 3, 4, 5 orbitals. Then comes S, and finally the p orbital. Since carbonyl is a strong field ligand, what happens? Pairing of electrons take place. Now these two electrons from the s orbital will be shifted to the d orbital. And as a result, now this orbital is free. Now count the electrons. 8 plus 2, 10. 10 electrons are all occupied in the d orbital. Now these orbitals, this s orbital and this p orbitals are all free. Means it is unoccupied. Now therefore, the lone pair from this carbonyl will be accepted in this orbital. How many carbonyl groups are there? 4. Therefore, 4 orbitals will be used to form this complex. Now this will be bonded with what? Each orbital will be bonded with carbonyl. So here carbonyl is present, here also carbonyl, carbonyl and carbonyl. Now these 3 orbitals are used for what? This 3 orbital as well as this orbital is used for hybridization. Therefore, its hybridization is sp3. 1 s orbital and 3 p orbital. P3, 1 s orbital, 1, 2, 3, 3 p orbitals. Therefore, its hybridization is sp3, and therefore its geometry is not tetrahedral. Tetrahedral. Now, one more thing that you have to remember is, now in the formation of the complex, here you can see that all the electrons are paired. All the electrons are paired. Now, if you don't have any unpaired electron in the complex, then please listen carefully. If you don't have any unpaired electron, here all of them are paired up, then such complexes are what? Such complexes will be diamagnetic. Diamagnetic. Okay? If they have unpaired, okay? Unpaired electron, then they will be paramagnetic. Please remember this. So we have discussed about the tetrahedral complex, taking example of nickel, tetracarbonyl, and here this is how you have to do this. You have to apply Pauling's principle, this to predict the geometry as well as its hybridization and whether it is diamagnetic or paramagnetic, okay, in nature. So let's take some more examples, and let's discuss about now octahedral complex. So now we are going to discuss about octahedral complex. Let's take an example first. So here we'll be taking the example of Fe Cn whole 6 3 minus. So here also you have to apply the way you did it for nickel tetracarbon. Iron in its zero oxidation state, that means whenever it doesn't have any charge, it has atomic number 26. So you have argon with atomic number 18. Okay, atomic number 18, and here what you have? Here you have d orbitals, s and p orbital. So here it is 18. After that, 2 will be occupied here in the s orbital. Then 1, 2, 3, 4, 5, and 6. So this is the electronic configuration of iron in oxidation state 0. Okay. Now in this complex, as I have taught you actually to find the oxidation state of Fe in our previous video. So here Fe in this complex, suppose you have the oxidation state of this Fe is X, then you have 6 ligands of what? Cyanide, and each cyanide carries -1 charge. Now this is equal to -3. Now here you have -6 equals to -3. Now whenever you take this -6 that side, then you get +3. Therefore the oxidation state of Fe in this complex is +3. That means from here, from neutral atom to be in the oxidation state of 3, it has to lose 3 electrons. Okay? So remember, you have to always find the oxidation state of the central metal atom or ion in the complex first. So here we have ion in the +3 oxidation state, argon. Now, one more thing that we have to note is whenever the electrons are lost, it has to lose from s orbital first. So, how many electrons does this Fe3 plus has lost? From Fe, it has lost 3 electrons. So, 2 electrons from here will be lost, and 1 electron from the next, the previous orbital, that is the d orbital, is lost. Therefore, here you have 1, 2, 3, 4, 1, 2, 3, 4, 5 electrons. Now this is vacant, as well as these orbitals are also vacant. Okay? So in +3 oxidation state, they will be having all unpaired electrons. Now again you have to see which ligand is present. Cyanide. Cyanide is also a strong field ligand. Please remember, strong field ligand. This is for your knowledge. Okay, this is for your knowledge. How you predict whether they form this inner orbital and outer orbital complexes. I'll be telling you that. Okay. See. So since cyanide is what? Strong field ligand. All these electrons will be paired up. It forces these unpaired electrons to be paired. Why? Because it is a strong field ligand. So in complex FeCN whole 6 3 minus, what will happen is the electrons, the unpaired electrons will be paired. So 1, 2, 3, 4, 5. Then you have p orbital and s orbital. So here electrons are paired. 1, 2, 3, 4, and 5. So these 5 electrons, they are paired. Now because of this, what we see is, these 2 orbitals are vacant. This is unoccupied, and as well these are also unoccupied. Now how many cyanide ligands are present? 6. So these 6 cyanide ligands will be overlapping with this remaining orbitals. Okay, so here you have what? Cyanide, here also cyanide, 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 and cyanide. So, which orbitals are used for hybridization? 2 d orbitals. So D 2, 1 s orbital, s, and how many p orbitals? 3. Therefore, its hybridization is D2sp3. Okay, D2sp3. Please remember it. D2sp3. And since here in this complex you can see that you have one unpaired electron, therefore it is paramagnetic in nature. So this complex is what? Paramagnetic. 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 And one more thing you have to know is, since in the formation of this complex, what has happened? These electrons are paired up. They are being forced by the ligand to be paired up. See, before the formation of this complex, all the d orbitals were what? Occupied by this unpaired electron. Now, as it forms the complex, this cyanide ion, it forces these electrons to be paired. Therefore, such complexes call them to be what? Inner orbital complexes. So we call them to be what? Inner orbital complexes. Inner orbital or low spin. Why low spin? If they are having unpaired electron, then their spin is high. Okay? So once they are paired up, this one electron pointing in the upward direction has plus half this spin quantum number value. The other one pointing downward has minus half quantum number value, that is spin quantum number value. Therefore, they cancel each other's effect, and as a result, we call them to be what? Low spin. If they are paired, then we call them to be what? We call them to be low spin complexes. Why inner orbital? Because the inner orbitals, which were previously occupied by these electrons, are being used by these ligands. Therefore, we call them to be inner orbital complexes. So let's discuss few more examples of these octahedral complexes, so that if you have any doubt, that will be clarified. Now, let's take one more example, that is CO NS3 O6, and here cobalt is in which oxidation state? It is in +3 oxidation state. So cobalt atomic number, you know, cobalt, nickel, copper, zinc. Therefore, its atomic number is 27. So now, by now, you must be able to write its electronic configuration. R180, then comes d orbital, then comes s, then p. So here, 2 electrons will be occupied in the s orbital, then the remaining will be occupied here. Because the electrons are filled singularly. So 20, 25, then pairing takes place. That means 25 to 27, which is equal to the atomic number. Now, since cobalt in this complex is in +3 oxidation state, we need to remove how many electrons? 3 electrons from a neutral cobalt atom. 1, 2, 3, 4, 5. So 3 electrons are removed from this cobalt atom. Therefore, 2 electrons from here and 1 electron from here. So 1, 2, 3, 4, 5, and 6. So this is the electronic configuration whenever cobalt is in +3 oxidation state. Okay? Now, here, whenever it forms this complex, NH3 whole 6 3 plus. Now here again the electrons are paired up. Okay, here you have to remember that these electrons are paired up. So 1, 2, 3, 4, 5, 6. So 6 electrons are paired up in the d orbital. Now how many ligands are present? 6 ligands. Now therefore NH3 will donate its electron to this orbitals. Okay, here you will be having NH3. This is also NH3, and NH3. Now here again you can see that from here onwards, how many d orbitals are used? 2, 1s and 3 p orbitals are used in the hybridization. Therefore, its hybridization is d2sp3, and you can find that here you can see no unpaired electron is present. Therefore, it is what? Diamagnetic. Okay, and once again these electrons are being forced to be paired, and the inner orbitals are also used. Therefore, it is known as what? The complex is inner orbital or low spin complex. Okay, why low spin? I have already explained. Now, for your assignment, you will be doing certain complexes. You will try to find all this, like what is the hybridization, whether it is diamagnetic or paramagnetic, and whether it is inner orbital or low spin complex. So your assignment, let me give you 1 or 2 complex as your assignment. The first one is FeCN whole 6 3, it is 4 plus, it is 4 minus. This part, the first, you try with this complex to apply this valence orbital, valence bond theory. The second complex that you have is Fe F6 4 minus. Okay, Fe F6 4 minus. Please try to use this valence bond theory and get whatever you are asked for. Now, let me give you one more example. Here, the example that we are going to take is CO. Please don't forget, please do it. The next example that we are going to take is COFE, COF6 3 minus, COF6 3 minus. So here, oxidation, this cobalt is neutral. Whenever it is neutral, I have already done the electronic configuration of cobalt several times. 1, 2, 3, 4, 5. 1, 2, 3. So in the neutral state, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. So in this complex, cobalt is in +3 oxidation state. 3. Therefore, it loses how many electrons? 3 electrons. 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, 2 and 1. So here you will be having 6 electrons in d orbital. Now in this complex, CO F6 3 minus this hybridization part, you have to know that F fluorine, all halogens they are weak field ligand. They are weak field ligands. Now, if they are weak field ligand, then they don't have this capacity to pair up this electron. Now, in the formation of this complex, these orbitals will be used. So here we have R1 with atomic number 18. After that we have d orbital 1, 2, 3, 4, 5. Then P, then S, then comes P, and again what comes? The d orbital 1, 2, 3, 4, 5. So here, since fluorine is a weak field ligand, therefore it doesn't have capacity to pair them up. Now this fluorine will be forming bond with this metal complex that is covalent by using this orbital 1, 2, 3, 4, 5 and 6. Why 6? Because you have 6 ligands. So this will be occupied by fluorine, 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 fluorine and fluorine. Now you can see that in this complex, which orbitals are used? 1 s orbital, 3 p orbital and 2 d orbital. Therefore its hybridization is sp3 d2, and you can see that it has 4 unpaired electrons. Therefore this complex is paramagnetic, and since these electrons were not forced to be paired up, therefore this is known as what? Outer orbital complex. It is known as what? Outer orbital complex. Outer orbital or high spin complex. Why high spin? Because you have so many unpaired electrons here. You can see that 1, 2, 3, 4 unpaired electrons. Therefore, it is paramagnetic, outer orbital or high spin complex. So with this, we come to the end of today's class. So whatever assignment I have given you, please do them and submit me in my WhatsApp number. Thank you.